Just two quick things. I lost my glasses when I showed up, so I can't see anybody's face beyond the second row. So if I don't recognize you, I'm sorry. And two, Christian specifically told me I was allowed to swear. So if you've met me before, I swear a lot. So right now, if you raise your hands, I will not swear, because I know I do it a lot. And there will be no shaming. Fucking great. All right. My name is Josef Bacik. I was a core developer for ButterFS. I have worked in the kernel for 20 years. I am a professional grenade jumper. I currently work for Anthropic, so doing AI stuff. Sorry, I will not do that again. So this is a talk about Systing. All right, so I do a lot of strange investigations, right? I tend to get called into problems that are just like, there is a problem, we don't know where to start. I use heavily a lot of tracing tools, just like the rest of us, right? So kind of the current state of affairs is perf. We all love perf record. You know, we can see percentages of where the CPU is and that sort of thing. I say we all, I am used to debugging these sort of things. So like perf is a first step, but if you've ever used perf, you know that it's not super useful if you are trying to debug something that's I/O bound, because perf is sample based. It just records events at a particular time and aggregates that and gives it to you. And it's like most basic form. Obviously, you can do a bunch of things with it. So you have to like augment debugging with a variety of other things. My favorite obviously is BPF trace. Love BPF trace. If you haven't used it, go look at the manual. The manual is awesome. They have examples. Always use BPF trace. It's perfect. Unfortunately, BPF trace does mean you have to know a fair bit about how the kernel is laid out and where the code is and how things work and that sort of thing. That's always sort of the drawback of these tools is I can use them because I know how the kernel works, but a lot of people have a lot of trouble using them, and that's totally understandable. Not everybody's a kernel developer. The other thing is libbpf tools. I love this. It's basically like if you used BCC way back then, this is like the more modern update of that. Basically, you have things like files slower, netstats, like things utilizing BPF to get really good fine-grained information. Like if you've ever read Brendan Gregg's blog posts, and he talks about a lot of the BPF tools, and so that's where these things are. Those are fantastic. These are what I would suggest if you are not a kernel developer and you're like trying to figure out where things are. Chances are there's a BPF tool, a libbpf tool that will help you narrow down what is happening. So like these are great, right? And then just kind of generally flame graphs. Again, this is another thing brought to us by Brendan. This is visualizing stack traces in a way that like helps us visually quickly tell where we're spending time. Like perf gave us percentage based and aggregated the stacks. And if you're used to that, then it's pretty good. But flame graphs are that way of like very quickly visually telling like, oh, okay, here's the problem. Right. So I kind of talked about this before, but like the general strategies that I have when it comes to debugging problems kind of starts at like the basics, right? You have top, you have SS, you have netstat, you have all of these tools that can give you snapshots of views into different subsystems, networking, file systems, I/O, memory, all of that kind of stuff. So you can always start there, right? And then you can move down into these domain-specific tools. Off CPU time, this is an example of the BPF tool. Like I use off CPU time all of the time as a file system developer because oftentimes we're stuck waiting for resources or the I/O or locks and that kind of thing, so that's really useful there. And then like obviously all of the sample-based workflows. The thing here for me is I don't know how often this happens to you guys, but I get pulled into things where the application developer is saying there is a problem and I don't know where it is, right? And the path between there is a problem and categorizing the problem is oftentimes huge, right? Like they can tell you simple app-based metrics and say like, okay, this metric has gone down, this latency has gone up. The problem with this often is that application developers don't necessarily understand how their application is interacting with the base system, right? And this is not like a slight against them. Like, we all have the thing that we're good at. I will never be contracted to write a Salesforce application, right? Because I don't understand it. And to that end, those guys don't understand what library call does what thing on the system, right? And so oftentimes we have application-specific metrics that encapsulate a wide variety of operations. It is a disk access, it is a network access, it is a call to a GPU, right? It is a variety of different things, and all they can do is tell me this number went down, or in the case of latency, this number went up. And it's up to me to tie this number to this set of actions so that I can then go down the set of actions and figure out what part is slow. This is a very frustrating part of my job. And about this time last year became even more frustrating because I was tasked with a problem involving training, AI training. This is when I was working for Meta. The fun part about AI training applications are that they are written by researchers in Python. And the researchers are brilliant in their domain, but they're writing Python that calls into a PyTorch, which is on top of Torch, which is on top of CUDA or Nickel or any variety of other things before they actually get to the operating system. So when I say, what are you seeing? They're seeing they say like, our training goes slower. Great. So like the training loop goes slower. What does the training loop do? Oh, it does a forward pass and a backward pass, and then it sums all the gradients. Thanks. That's extremely helpful. I got all of that. Perfect. And this is the problem, right? Like oftentimes application developers can tell me what they know about, but like I have no idea what their thing is doing, and I have no idea how to translate that into domain specific information. So as applications get further and further removed from the lower level operating system, the more and more difficult it is to be able to get a full view of what is happening on the system. Jesus, sorry guys. The other thing that makes this kind of difficult, right, is we have a variety of different languages that get used. And this isn't just like a Python problem. Python is just the guy that I'm beat up right now. But you have Rust, which like, and I do this, right? Like you just implement, oh, this crate does the thing that I need. Use crate, and the crate could be doing any number of things underneath the hood. C++ does this. Like everybody does this. The only people that don't really do this is C, and they have their own issues, right? So this is not a slagging of the application developers. This is just modern software development. We need to be able to move quickly and reuse pieces. I think that using frameworks like PyStack and like Tokyo, for example, for Rust, like all of these things are really, really important. And it abstracts out a lot of these things that are very difficult for people to keep in their heads. And it allows for more and more people to do different things. It just makes my job a lot more difficult. So, Systing. I started writing this about this time last year to try and debug problems, because the thing that I consistently ran into is I have a set of things that I start to look at. I write the same BPF trace script every time, because Lord knows I can't fucking save it, to like figure out scheduler latencies. I write the same fucking BPF trace to figure out network latencies, right? And so you kind of do the same thing over and over again. You get annoyed with yourself. I did not set out to write my own tool. I really, 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 really hate inventing things. I really hate starting new, because frankly, I jump from thing to thing to thing, and I don't have the bandwidth to maintain and like build a tool that people can use, right? That's just not my skill set. Unfortunately, this is a concept that hadn't really been explored a lot. The thing that I always do with my tracing is I'm looking at wall time. Like, samples are great, and flame graphs are great, but it doesn't mean anything outside of the context. The way I explained this to somebody was like, if you're driving your car, and you get in your car and you drive to work, like, sample based is like every second I'm checking to see what your speed is, right? And so I can kind of get an idea of what it is throughout the entire drive. But we don't ever look at the individual samples. This is perf, right? We get like the aggregate. So now we have individual samples, and now we average it together, or we bucket it. We'll put it in histograms, right? 10% of the time I was 0 to 5 miles an hour. 30% of the time I was like 25 to 45, right? Those sort of things. But this gives you a really warped sense of like how the drive went, right? If you all of a sudden for 2 seconds decide to speed up to 130 miles an hour, and then go right back down, you're going to miss that information most of the time with most of the tools. So I always rely on wall clock profiling, because I want to know exactly how long operations took. I don't really care how often I ended up in this thing, in this particular stack trace, because I want to know what part of it was taking forever. And this is another flaw that I find with, especially with like engineers that are not as experienced in this, is you will see a flame graph of something, and it kind of like points at one leaf node of a particular stack trace, right, as being the problem, without understanding that deeper down in this call trace, it's actually a loop, and you just happen to be getting lucky by catching the same spot. But the problem is the loop is taking forever, but this gets lost in the noise. And so this is where it's important for me in a lot of my tracing. I always did I have a script in my debug scripts GitHub repo that you literally tell it a function and then the child functions, right? And I use this all of the time, because it's like, okay, if this function is taking a long time, is it that we are calling this function over and over and over and over again, and it's taking up this percentage of the time, or is it we're getting stuck somewhere else? And this way you can get a clear view of like, okay, I spent 4 seconds in this function, and 3 of those seconds was spent in this function, and 1 of the second or 0.1 second or whatever was spent in the rest, and it really helps you kind of get down. So this is the idea of the wall clock profiling. Applications do not behave the same way all of the time. Let's go back to the training example. So I'm gonna check time. All right, we go back to the training example. They have the training loop, and then they have a summary spot. And the training loop does 3 different operations, right? It's like the forward pass, right? It does a bunch of math, and then it passes all of its math back to all of its peers, and it does a bunch of math on all of its peers' math, and then it puts it all together and sums it up, and then it syncs the weights across the entire model, and then it does it again. It just does this over and over and over again. And then sometimes it checkpoints, because hardware is unreliable. I will be kind about that. So you have to consistently take snapshots of the work that you're doing, so when that unreliable hardware behaves the way you expect it to behave, you can restart without losing all of your data. So you have this thing that is kind of behaving, and then sometimes it goes off and does other things. And so you need wall clock profiling to be able to clearly delineate where in the application you are when you're experiencing the problem. Because you can say this part is going slow, but if you profiled in that gap that I talked about, where you're not actually doing any of the training, you're going to have a completely invalid view of what's happening. Or if you record for multiple training loops, again, that gap where you're not actually training pollutes your data. So it's really, really important to be able to see where you are in the application and look at the data in that time, as opposed to record an aggregate and then review after the fact. Sorry, that was a side quest into wall clock profiling. And this isn't like, I didn't invent this bullshit, right? Like, Andre, who, was one of my colleagues at Meta, who works on libbpf, brilliant guy. He and I kind of like came to this sort of like idea at the same time. And he has a tool called wprof, which does essentially what Systing does. But obviously he's smarter than I am, so it has some great features that are kind of like different from me. Systing I wrote in Rust because I wanted to. I was bored. I wanted to learn it. It was a good excuse. I use in the vein of not reinventing the wheel, I use libbpf rs, which is a Rust, idiomatic Rust wrapper around libbpf. So you have the libbpf sys, which is just the what do we call it? The bindings, the C bindings to actual libbpf. And then you have libbpf rs, which provides like real Rust objects and things around libbpf sys, so you can use it. It makes building libbpf projects really easy. And then obviously I use BlazeSim, which is another colleague from Meta, Daniel, who and this does the symbolization for stack traces. Oh, also I didn't put it up here, which is silly of me. Another thing that I use is called PyStacks. This was open sourced from the Meta tool Strobe Light, which is I will continue to do this. I've only been gone from Meta for like a month. It is their profiling tool inside of Meta. And this is how I get Python stack traces, which is, if you've used PySpy, like that's kind of the only tool that I know of right now that does like sample-based stack trace aggregating for Python. Previously, like if you use perf or whatever, you just couldn't see where you were in Python, which has never been a problem for me until AI things, where I needed to be able to tie all the way back to the original Python call that was causing the problem. So, to differentiate myself from wprof, because me and Andre like do kind of similar things, and we had similar ideas. wprof is really, really powerful, and Systing is really dumb. So you're meant to be able to just run Systing just out of the box and get a general view of what the system is doing. wprof, Andre has added a lot more of the fancier flow type tracing that's available. And I can't talk about Systing without talking about Perfetto. Systing is basically just a Perfetto trace generator. Perfetto is a project from Google. Screenshot here is the tracing side. Perfetto is like 3 different things. It is the trace collector. It uses ftrace for this. You can use Chrome, like it'll grab Chrome stuff. It's used in Android a lot. Like if you're an Android developer, you probably are pretty familiar with Perfetto. You can like tell it to go and trace the Android system, and it'll gather all these stats and all these things. and then you can use it. The reason I didn't use the Perfetto tracing thing and wrote Systing instead, there's a variety of reasons. One is the recorder uses ftrace. Ftrace has a lot of fun gotchas. I've used ftrace forever. I've added things to trace command. I love ftrace for normal stuff. But as far as like on demand, in production, high usage profiling, ftrace is entirely too heavy and loses things. And additionally, like the way they package it is just like not possible in production. Oftentimes I'm pointed at a machine that has a problem and I can't just like YOLO copy Perfetto's giant busy box single binary thing into production, but I can take Systing, which is very small, and copy it on there, generate a trace and copy the trace off. The other part of Perfetto is the part that I'm showing here is the UI. If you do any tracing or do anything at all, look into this because you can do all sorts of custom visualization. When I started writing my tooling, I didn't know about Perfetto, and I iterated a lot on how to visualize all of this data, because at the end of the day, like, this is a lot of data, and it's very difficult to like figure out how to visualize it. Perfetto is awesome, and there's so many people that have like custom track building and custom things. Perfetto will read that and visualize it for you. It's amazing. In fact, the AI guys, all that gradient shit I was talking about, like they can visualize all of that. It doesn't mean anything to me, but it's beautiful. Demo, right? So we're going to talk about this. Well, I'll do this actually. So this is what it looks like when you use Systing, right? I have a variety of things here. Some of them I'm not showing. I'm going to show kind of like the more interesting things that I find cool, and then I will show you how to use it and then kind of what it does, right? Right here, I'm for this trace, I didn't record the scheduler stuff. I will do that after this. But one of the big things that I've used Systing for in production and before I left Meta is it shows all of the scheduler events across all the CPUs. This was hugely useful for the SCEDEXT team because oftentimes it's hard to reason about what your scheduler is doing and if it's doing the correct thing without it being able to like visually see where it's moving tasks. And this allowed the SCEDEXT team to kind of like iterate really quickly because it visualizes where the tasks are. You can click on it and get annotations about scheduler latencies, how long it took to wake things up. I used it to debug a problem where SCEDEXT was delaying kblockd from launching, and you could really clearly see this where the task would go to sleep and would be asleep for 3 or 4 seconds waiting for I/O randomly, right? And with Systing or with Perfetto, the way Systing records the scheduler events, Perfetto will show you who woke who up, and you can see like, oh, okay, kblockd is the one that woke us up. Now I can click on kblockd and go see what it was doing, and it'll show, and it showed kblockd was stuck in runnable for 3 seconds, which means it was scheduled, like it wanted to run, but the scheduler wasn't putting it on the CPU. And from that, like a task should never be stuck in runnable for 3 seconds. The scheduler has messed up if it's done this. And it was like, oh, okay, there's a problem with this SCEDEXT scheduler with tasks that are pinned to a certain CPU. kblockd pins its tasks to CPUs, right? And so it makes weird interactions like that. Weird interactions like that really, really easy to spot. This is one of the things that I can do is I record stack traces. Perfetto won't do this or can't do this on Linux out of the box, so this is unique to Systing. Andre does this with wprof, but I think he does it himself, where he actually generates the flame graphs himself. I might be wrong on that. I don't do that. Perfetto has this ability, so what you do here is, like, this is the per process, and this is like per thread, right? And so you can just drag and select, and it'll generate a flame graph for the selected area. So again, this idea of like, oh, okay, this part went wrong, and now I have the stack traces, and I can get my flame graph for the part of the application that I know went wrong. And instead of doing something like this, so if I do like all of this, right, this can give you a warped sense of what is happening. If I did this with like a training job run, this would end up looking really weird, right? And then if you were doing this with perf, all of these blank spots where we are not on the CPU, you would have events there for it not being on the CPU, and that would further pollute your flame graphs. So if you did this just with perf, all of these gaps would be filled with a sleep. And now instead of the flame graph showing like actual things that was actually happening on the CPU, maybe suddenly you have 40% of it showing that it was asleep, right? Which can be useful if that's what's happening, but a lot of times you don't really care about that. I also, like, these are custom things that I did. You can like track syscalls. I use this to kind of like figure out what's going on like with an application that I don't know. And again, you can do things like select and see like, okay, this was doing futex, ioctl, pol, and then like breakdown of the duration, average, how many occurrences and that sort of thing. So, okay, I got 3 minutes. So we'll do this and no. I'm going to turn off stack traces because I don't know what kernel I'm in. There was a bug in 6.15 and it'll lock my system if I do stack traces. Is this going to work? All right, hopefully this doesn't lock my machine up. So like this is, like I said, the very basic thing. This will give you all of the scheduler stuff. This will give you the stack traces. It doesn't give you any of the fancy special stuff. Let's go down here. All right, this is the scheduling thing that I was talking about. So again, you can kind of see like where the tasks get up. Like these CPUs are kind of more heavily used, which makes sense. This is a framework machine, so it's the Intel one, so it's big little. The big CPUs are 1 minute. All right. So yeah, I'm going to run through this really quick. So this is kind of what I was talking about, and like I said, okay, we'll ignore this because I filter out Systing and it makes it look weird. So like, there's Claude or whatever, and you can kind of see these are the different scheduler stuff. So it shows you running, runnable, and you can zoom in. Right, and this is kind of useful, right? So runnable, right? Like that's 7 microseconds scheduler latencies, right? So it makes it really easy to like pick out scheduler latencies and that kind of thing. I also record like IRQ stuff, IRQs, or maybe I have them off, and soft IRQs. Nothing was happening on this machine, obviously, but it can be useful for like tracking things. All right, sorry guys, I'm out of time, but, oh wait. Am I out of time? I got 2 minutes. No, I'm out of time. Yeah, sorry. All right. Thanks, guys.